Now we're going to build on the ideas that have been sort of constructed now about how electrons are arranged. And we're actually going to compare different kinds of properties of atoms, including sizes and other behaviors, as they, again, compare to each other across the periodic table. So that's what we're going to talk about here, periodic trends. You also will hear this being referred to as periodicity. So the way this works, there's going to be a couple of trends we're going to look at. First of all, we're going to look at how the protons and electrons are arranged, and also the trends that occur. Something called atomic radius, ionization energy, electron affinity, and then finally electronegativity. And each of these, again, has its own unique properties, and you'll find that really a lot of this is based and rooted in some of the same fundamental ideas. And we're about to go over that fundamental idea. So it's really important that you understand some of these concepts that we introduced first. Before I get into those fundamental ideas, one thing I want to mention is that a lot of times we'll use some language here which isn't necessarily appropriate, but they're useful as analogies. However, I do want you to use a scientifically appropriate language. So, for example, we'll use stuff that has a lot of human sort of emotions and human needs and wants, and that's not really, again, appropriate for atoms which don't have human needs and wants. For an example, you might talk about this language right here saying an atom wants another electron to become stable. Well, again, no atom really wants anything because atoms don't have needs and desires where they can state things like they want something. But instead, you would say something like it is energetically favored to gain an electron, or the atom achieves stability by gaining an electron. All right, so it's not, again, about expressing humanizing feelings, but instead just facts. Same thing with this next one. It's harder to remove an electron, which you'll hear from time to time. It's harder to remove an electron. Not really that it's harder. It's just that it requires more energy input. All right, so there's some amount of this language that you need to be able to apply that reflects just these sort of stoic, unfeeling actions. Okay, now here's the fundamental part of it. It's all about this pulling proton power, pulling power of the proton. First of all, you should know that there's positively charged protons, and they're hanging out in the nucleus. And they're pulling on these electrons. There's this sort of attraction. Now, again, you kind of phrase this in different ways and have a couple of different perspectives. The most important thing we need to think of is having these protons in the center that, again, attract those electrons on the outside. So as you can imagine, the more protons that are present, the stronger the pull there is on the electrons. So as you go from left to right across the period, right? So you have lithium on the very far left, then Be all the way across to neon. You're going to have more and more protons. Therefore, you're going to have more pull on those electrons as you compare them from atom to atom. Also note that whenever we say comparing element to element, we're really saying atom of an element to the other atom of an element, and not really just atoms. Now, of course, that seems pretty straightforward, but another thing we have to consider is that the protons, more or less, are all the same, right? They're all in the center, they're all hanging out in there, but the electrons are not. And we discussed this at length, is that all the electrons that are assigned to an atom, well, they're not, again, in this uniform way. They have different levels and different arrangements and whatnot that they're assigned to, so we actually don't treat them all equally. So we need to define these electrons, or at least categorize them as either valence electrons, which you've seen here, or shielding electrons. The word valence, of course, these are the ones that are the outermost electrons, either the furthest from the nucleus. So in this diagram on the right here, the valence electrons would be these that I'm going to highlight in blue. Right? This is a valence electron, this is a valence electron, this is your valence electrons. Right? So this, again, counts as your valence electrons. Now, your shielding electrons, right, these are not your valence electrons. These are the ones in the center. These are closer to the center. These are not your outermost ones. And these right here, again, are ones that you can probably imagine, not only visual, but just sort of imagining the energy levels being full. The ones here, these are shielding electrons, and so are these that I'm very, very roughly highlighting. All those are your shielding electrons. And what they do, again, is that they're protecting, it's shielding, right? They're protecting the outer electrons from the nucleus, from the big bad protons. So as protons, their pull on the outermost electrons here is not as strong because these shielding ones, for whatever reason, have this effect where that kind of blocks, kind of acts as a physical barrier between the protons and those electrons. All right. So let's kind of see how this sort of looks, or at least how it applies. Let's go and take a lithium on the left, fluorine, an atom of fluorine on the right there. I've got a couple of protons, a couple of electrons, and notice how, again, you kind of split it up. We're in the middle, we have 3 protons here, which is not really explicitly written, but you kind of assume that they're there. And you have 2 shielding electrons and 1 valence electron, whereas fluorine over here, it's actually got 9 protons. But again, it has 9 electrons, not all of them equally assigned. You have 2 shielding here and 7 valence electrons out there. So which element do you think is able to pull harder on its electrons. Even more specifically, you can even say how hard does it pull on its valence electrons. We'll abbreviate that val. So when you look on the left, right, you have 3 protons. That's fewer protons. When you look at fluorine, that's 9 protons, a lot more protons. So there's definitely a lot more power there. But also, the two of them have the same number of shielding electrons. So the amount of buffering, the amount of kind of blocking that can happen is still the same. So if you have 9 protons only being blocked by 2 versus 3 protons being only blocked by 2, that means the fluorine's protons here are able to pull and draw and like pull these in a little bit harder, right? So have a stronger attraction towards them. Whereas lithium, right, it's only got a little bit because it's got the 3 protons, fairly weak in comparison, and only being blocked by 2 electrons. Now, visually, of course, this is not exactly accurate, right? We're not saying that these 2 electrons are just physically in this location the whole time, and the fluorine will then have easy access to these electrons that are away from it. No, of course, this is again a Bohr model, which of course is not accurate, and this is not a static image. In reality, it's supposed to be some big dynamic lobes of electron clouds and stuff. So it's a lot more complicated, but that's why we use this as a nice visual to help us understand that idea. Atomic radius. Now, this is kind of the second trend. So that first one we just went over, that's the fundamentals behind it. This is going to be the first actual trend. So let's go ahead and define this one. Atomic radius. It's the radius, which is half the distance between the nuclei of identical atoms that are bonded together. Okay, now, so I think you'll probably appreciate sort of the difference here between what we theoretically want to do and what's actually used. So let's say we have an atom and represent it like this. You can imagine the radius, right, would just be that distance from here to here. But as you know, atoms don't really look like spheres. Atoms aren't really just circles that you can just draw a straight line from. Furthermore, right, these clouds that I'm air quoting, you can't see me, but these clouds where the electrons are located are also, there's not a concrete boundary where it definitely ends. It's a probability. It's a range of things. So it sort of just eventually fades, but that's not something that we can necessarily just draw a line to and make it a radius. So the best thing we can do is to take the distance from here to here, right, from one nucleus to the other nucleus, and split that in half. Make sure, of course, that we're talking about the same atom, so that when you have 2 chlorine atoms, it's not like chlorine and a fluorine, and then looking at that distance. That doesn't make any sense. Also notice this is also typically measured in PM, which is not the half of the day, but of course represents the picometers, where pico represents 10 to the minus 12. So here's a little mini periodic table, kind of cut out a big chunk of the D block because they're not as useful, or at least their system is a little bit different and not as easy to identify. So in this case, we're just going to look at the S block and the P block, right? So this right here is my S block. You can see the 1A, 2A groups that constitute my S block, and my P block over here. And basically what we have here is a couple of atoms, and you can see they have not only the element names and such, but they have a little sphere here that kind of shows their relative size, and a little number to represent their atomic radius. Now, if you notice, generally speaking, you'd see some trends. Now, how we usually do this is we'll talk about going down a group, right, and then going across from left to right. So let's go ahead and talk about going down a group. So if you look down each group, right, this group, this group, this group, so on and so forth, what do you notice about the atomic radius? It gets bigger and bigger. Right? And that's definitely just a fact that we know. We know that this happens. As you go from left to right then, right, going from row to row to row, right, this one you notice they get smaller and smaller. This is worth memorizing. Right? You have this pattern where going from top to bottom, it gets bigger, from left to right, it gets smaller. And of course, as you can imagine, we're going to kind of get into why that's the case. So one thing you should also look out for is understanding what kind of explanations we're looking for. We're looking for the atomic level explanation for why this trend occurs. So let's do that. But first, I want you to take a look at this. We notice how you kind of have a bunch of these charts. I want you to think about how this graph right here shows that trend that we just described, right? So going from top to bottom down a group, going from left to right across the period, that the trend is that they increase and decrease respectively. Now, let's talk about this. Why exactly does that happen? Well, let's go across the period, and we've actually discussed this before. Remember, as you go from left to right across the period, you have more and more protons, right? From element to element, it increases by an atomic number of 1, which means one more proton. And so therefore, you have more and more positive pulling power. So that means electrons are being drawn closer to each other. But also, one more thing to consider, and it's like another little side point here. What happens to the number of shielding electrons as you go from left to right? So remember that these electrons, as you increase it from one to the next, going across the period, you're actually only assigning electrons to the valence shell. You're only assigning electrons to the outermost shell. And so you're not really going to add any extra blocking, shielding electrons. Those shielding electrons, that number stays the same while the number of protons goes up. So in fact, you actually see that because shielding electrons stays the same, right? That's definitely a very sloppy way of saying shielding electrons remains constant. Because shielding electrons stay the same, and you're adding both protons and valence electrons, those valence electrons get pulled in more by those protons. Right? Therefore, when they get pulled harder, right, pulled in harder, they get drawn in closer, making the overall radius smaller, making the overall size of the atom smaller. What about going down a group? Well, again, like I said here, the radius increases, right? So it gets bigger and bigger going down any given group. Well, it turns out, right, as electrons are assigned to a larger energy level, they get actually assigned further away, right? Because going from period to period down a group, you're actually assigning something to the 1s, 2s, 3s, the 2p, 3p, 4p, right? You're increasing the energy level, and that means they're getting bigger and bigger. They're just being assigned literally to an energy level that's physically larger from the center. It also has an increasing shielding effect, right? Because once you start assigning electrons out here, you're assuming that you basically filled in all the electrons in here as well. So as you start assigning electrons out here, that not only are physically located further away, but on top of that, you have more and more shielding electrons that block the increasing number of protons. A quick visual here of explaining what we just saw there, right? So lithium versus fluorine, you have a lesser number of protons, shielding electrons is 2, more protons, shielding electrons is 2, so these valence electrons get pulled in tighter to make it smaller. These protons don't pull as much, and therefore it's bigger. As you go down a group, so lithium is at a higher higher up on the periodic table than sodium. Notice again, so 3 protons here, 11 protons here, and you can see that the number of shielding electrons also goes up when you compare this one valence electron being pulled by the 11. This one right here being pulled by the 3. It's really hard for this 11 to really get through these 2 complete rings of electrons to get to that one. So that's why it also doesn't pull as hard. And then, of course, it is physically just larger. So the outermost energy level is larger. So that's why the radius gets bigger as you go down a group. Let's talk about ionization energy. This one's going to be a similar idea that relates to this idea of pulling power. Ionization energy is the energy required to remove an electron from the gaseous state of a sample of atoms of a single element. Okay, all right, that's a lot of words. So I'm going to skip down to here to the bottom part where it says, terrible underline, where it says, that's also a terrible underline, where it says, essentially, a measure of how strongly the protons of an atom hold on to its outermost electrons. So this is kind of how it works, right? So let's take a look at this atom. This is lithium. You've got 2 inner electrons, these shielding electrons. You have the one outer one. And basically what we're saying is how much energy does it take to remove this outermost electron, to remove that one? Therefore, resulting in lithium positive, right? Lithium plus. So that's effectively what ionization energy represents, the energy required to ionize the atom. And of course, you're thinking, okay, ions can be positive or negative, but specifically this is saying that if you were to remove an electron, what would the energy be? Therefore, you're talking about making a positive ion. Now also notice that we're not talking about lithium, or we're not talking about ions always being the kind that we expect. For example, if you talk about magnesium, right? Magnesium will generally become magnesium 2+. We're not talking about that. We're talking about just magnesium becoming magnesium positive, right? This is kind of a theoretical construct. Of course, this is something that you can measure, but in terms of what we're trying to accomplish, really just trying to take off one. Here's a sample reaction equation. You can see that you have the atom X, you have X plus, and you have E minus. And kind of associating this with another type of reaction, it's kind of like an oxidation, right? Oxidation is losing an electron. So we're basically oxidizing an atom and making it positive. So let's talk about this. Going across the period, the ionization increases. Right? Going from left to right, the ionization energy increases. And let's remember, more protons, more positive pulling power. And that means electrons are held tightly by the protons. So you can imagine those protons are having a stronger hold. And so how much energy is it going to take to remove something that's being held by the protons versus something that's not being held as much? It would take a lot more energy to remove a more tightly held proton. Therefore, you have electrons being held tightly, more energy required to remove an electron. On the going down a group, right, going from top to bottom, the ionization energy decreases. And you kind of imagine this. We talked about this earlier, about the fact that protons can't pull as much going from element to element down a group. Right? So ones at the lower end of the group compared to the ones at the higher end. The ones at the lower end are just not as able to hold on to its outermost electrons. So you're actually going to find that there's going to be less energy required to remove an electron. This is kind of a visual here. Again, we're trying to get rid of this electron. We're trying to get rid of this electron. How do they compare? Fluorine is going to be much higher because it has a much stronger pull than the pull it has on this one. Whereas for lithium, the pull it has on this one is actually stronger in comparison to this one, which is much weaker since it's further away and can't hold on to it as much. So the ionization energy for lithium would be greater than the ionization energy required for sodium. So it's all relative, right? Lithium is weaker than fluorine, but then lithium, the ionization energy is actually higher than for sodium. And to wrap it up, we're going to go ahead and finish off by looking at this. By looking at this chart, you notice again that there's a x-axis, y-axis you might want to look at that kind of shows the trend of what happens for ionization energy. So make sure you can track going down a group, going across the period, what exactly happens with the ionization energy, and that this shows that pattern. All right, that'll do it.